Hello, my name is Professor Al Bovik. I'm the director of the Laboratory for Image and Video Engineering at the University of Texas at Austin. I'll be speaking to you today about a topic in digital video processing, specifically the title of my talk, which let me first get my screen share going. There we go. Is speeding it up, perceiving higher frame rate videos. Well, I'll explain what I mean by that and why it's important as we go. This is a joint effort between myself and my students in the Laboratory for Image and Video Engineering at UT Austin and engineers at YouTube, who I will mention later. So, frame rate, why is that important today that we consider different frame rates, higher frame rates? Well, it's important because of another concept called video quality. I'll tell you what I mean. Well, first of all, video quality means the quality of a video as it is perceived by a human viewer. This is something we would like to be able to predict accurately for many different reasons in video engineering and in the area of computer vision. And I'll explain some ways that these models are used shortly. Some very good models exist, some of which you may have heard of. One is called the Structural Similarity Index, or SIM. Another is called the Visual Information Fidelity Index, or VIF. Another one is called VMAF. The first two were developed in our laboratory. VMAF uses tools that we developed, but was developed by Netflix. These three algorithms today are currently used to control the quality of more than 3/4 of all internet traffic in the United States today, and a substantial amount that is growing elsewhere as well. So why is it used this way? Well, the main reason why is that video dominates the internet. More than 80% of all the moving bits on the internet today are video. Isn't that amazing? It's certainly uh, nice for my laboratory. We're very excited about that, that we're in a very relevant space. Even though there's algorithms that are successful at predicting the quality of videos, well, why are they successful? Well, they're mostly used, the biggest application is to control the amount of the compression of videos that are streamed across the internet. That's not the only way they're used, but it's maybe the biggest way that they are used. And the more you can compress videos, then the more efficiency that you can achieve in terms of bandwidth usage. And this is very important today because videos keep getting bigger and bigger. We have UHD, HDR, and now high frame rate. So the volume of videos continues to expand and will continue to in the future. So the more that you can compress the videos while maintaining their perceptual quality, the better. So even though there are successful algorithms that are used today to control video codecs, there's still a need for much more research. First of all, HDR I mentioned a minute ago, there are algorithms needed that can better predict the effects of HDR or lack of HDR on videos. Another direction is, how does resolution play a role? Uh, are there different tools needed that can, predict the quality of UHD videos better than existing algorithms? And of course, the area of virtual reality and related things, AR and, well, generally XR, where we have this immersive environment and the video surrounds you and you can move your head and eyes around, different models are going to be needed there as well. We're working with Facebook on that problem today. And today's topic, high frame rate video. This is a topic that is really coming on fast because of the kind of content that is becoming popular over streaming media. Uh-oh, newsflash. Let's see what's going on.
We have major breaking news. The world is under alien invasion. We have dozens of reports.
Video quality measurement has become increasingly important as viewers have become more sophisticated and sensitive to distortions such as noise or blur.
Reporting sightings of at least 20 to 30 large UFOs.
Television distortions often arise when bandwidth limitations prevent high-quality information from reaching the receiver.
Panic and panda.
In extreme conditions, internet congestion can cause high-quality video content to...
Let's go to live video of the UFOs right now.
Oops. Well, hopefully that gives you some idea of the kinds of distortions that occur and that we would like to avoid when streaming videos or watching television. Compression is kind of the big one in this context. So I keep mentioning frame rate. So a question we ask, since higher frame rates are becoming available, there are cameras that deliver very high frame rates, displays, and there's increased interest in streaming higher frame rate videos. Why is that? Well, because viewers like you and me are becoming more interested in watching videos that require higher frame rates. Those kind of videos typically have a high degree of motion, such as sports, watching NBA basketball or the Olympics, or anything where there's a lot of fast motion in the video or where the camera is moving quickly. High frame rate becomes very advantageous for these kind of things. Let me give you an example. I'm going to show you two videos. The first of which is at 60 frames per second. That's a higher frame rate, but not very high frame rate. And the second one is at 24 frame rates, which is kind of like when you go see the movies. The camera is moving in both of them. They both have the same level of compression, and it's very little compression. So compression does not supply much distortion here. It's all about frame rate. So here's the 60 frame per second video. You can see that as the camera pans around, everything looks pretty smooth. It's not perfect. You know, your eye might find some, some visual distortions or some little bit of jerkiness and so on, but not too bad. When we look at the 24 FPS means frames per second video, depending on your network and your monitor and so on, hopefully you're able to see this. This one suffers from a distortion, which is a jumpiness over time. It's called stutter. And this is because it's not a high enough frame rate to represent these high motions of the camera. Sometimes it's also called judder, but stutter is more correct. This definitely affects the quality of videos, and we would like to avoid this by having higher frame rate videos when there's high motion. Here's another video where there's less motion. There is motion, there is no camera motion, there is some object motion. Here it's 60 frames per second. You view this and you say, wow, that's a pretty nice video. Hopefully you can agree, as this is recorded on Zoom and then transmitted over your local network when you watch this from the school. Here's the same video at 24 frames per second. This is also not bad. There is some faster motion, and the movement of some of these leaves may seem a little bit jerky to you. That's a little bit of stutter. But generally, there's not as much motion in this video, and it's generally of a higher quality. So again, motion can affect quality very much. So as we move towards higher frame rates, we're going to have to worry about these new distortions. We're going to have to also wonder about, well, why study this? Why would we change frame rate when we're streaming video? Well, there's some good reasons for doing that. Also, how do we perceive frame rate changes, and how is it affected by temporal masking? Well, what is masking? Masking is when the distortion is hidden by the content. Sometimes you don't really see compression because a picture or a video has a lot of activity in it. So temporal masking is, well, can motion hide distortion? Well, not too much, as it turns out. Motion actually increases distortion in this context. So anyway, there's a lot of aspects to this. How do we learn about how we perceive quality as a function of frame rate? Well, there are limited tools out there. There are a couple of groups who've studied, what if we change frame rates? But we noticed that there was a large gap in a practical database, one that would combine frame rate changes with compression, which is what really happens out there in the real world. There's always compression when you stream videos, and that compression is varied as a function of bandwidth conditions and perceptual quality and other things. So if we inject frame rate changes in there, that also will have to have an interplay with changes in compression. I want to point out Pavan, who was the graduate student who drove this work, and our collaborators at YouTube, Yilin, Neil, and Balu. And by the way, thank you for having me at this school. I started right off into it, but I don't want to forget, thanks for having me. Okay, so why have this new subjective database? Like I said, there's a lot of databases out there. We've created 20 databases of various kinds over the last couple of decades, but very few of these have been devoted to the study of high frame rate, and none of them where frame rate and compression are both varied, which is the practical scenario. So we created one. We also had human subjects look at these videos and supply their ratings of quality. That's very important. And why? Well, because in the end, we want to use a database like this to create algorithm tools that can predict what a human would say is the quality of a video as a function of compression, of frame rate, and the content of the video. If we can predict what a human says, we'll deliver better quality videos to the consumer while saving enormous numbers of bits. Billions of bits a year, many billions of bits a year, which is very important because videos keep getting bigger, our networks get bigger, but it's hard to keep pace with videos, which now occupy most of the bandwidth available. And, we also save energy. The internet uses, about 5% almost of all energy consumption, if you can believe that. And video has a lot to do with that. So we can improve environmentally as well. So when conducting a human study, we have to have a lot of humans rate the videos. Why? Because like I found on this fortune cookie, as I was contemplating these topics, everything has beauty, but not everyone sees it, at least not in the same way necessarily. Although, as we'll find, humans largely agree about video quality, including when frame rates are considered. Okay, well, before collecting human scores, we first collected the video data. We collected 16 very high quality videos, all of them which were uncompressed, undistorted, and were at 120 frames per second. So that's today, as high as we can imagine streaming today. One day, maybe it'll be higher frame rate than that for some certain contexts. Anyway, we took each of these 16 pristine videos, very high quality contents, and we temporally downsampled them from 120 down to 5 other frame rates, 24, 30, 60, 82, and 98 frames per second. Now, it may seem odd to you that, these latter two, 24, 30, and 60, these are very common numbers for frame rates, but 82 and 98 are not. Why did we do that? Well, first of all, we wanted to fill the gap between 60 and 120. To create a better model, it's best to have data points throughout the range of possible frame rates, because eventually our goal is to collect all this data and then develop models, predictive models based upon that data. Secondly, well, okay, why not pick 80 and 100, say? The reason for that is the very high quality, high frame rate video monitor we used actually has refresh rates of 24, 30, 60, 120, 82, and 98. We match the refresh rates of our monitor. That way the monitor would do no additional processing to change the frame rates to the refresh rates that it supports, such as interpolation. We don't want the videos to be changed at all by the monitor. We want to understand what they are completely. After downsampling them in time, meaning reducing the frame rate, then we compress them. How do we compress them? Well, I'll get into that in a second. We use one of the major video codecs. But first, about the source videos. We, as I said, collected 16 videos, each 120 frames per second. 11 of these are from the BVI HFR database. That's from David Bull's group in the UK. These are 1080p videos, the original pristine videos, but they're all 120 FPS. We're also fortunate to get 5 videos from Fox Media Sports, all of which are at 4K. That's the total of 16. This shows some sample videos from all of these. You know, we have sports videos and we have other videos. There's a lot of motion in these videos, which is kind of the direction that we're interested in. Why did we consider both 1080p and 4K? Not because we were considering the effects of changes in resolution. In fact, no video was viewed at both resolutions. Okay, we did that. We weren't interested in that for this study, even though that is an important problem. It's been studied already by us and by others. We wanted to focus on the temporal aspect, but we also wanted to represent both resolutions because 1080p remains the dominant streamed video resolution, but 4K is coming on very fast. After all, you go to the store, what do you see on the wall? 4K televisions. So we wanted to do both. We made some measurements on the original videos. These are some classical measurements that are typically made to describe the content of videos. The first is called the SI, or spatial information. It's really a measure of spatial activity, and it's just the Sobel magnitude, which is an edge detector operator. We also measured the temporal information, or TI, and this is just the sum of the absolute frame differences between adjacent frames across the video. It's a measure of temporal activity, how much the video is changing over time. And then a colorfulness measure developed by Sabine Sestrunk's group. And this measures how much, color, vividness of color is in a picture or in a video, and it's widely used as well. We only use these just to show that our videos have a broad spread of all of these values, and hence are likely to be very representative. So we have videos that are very colorful and less colorful and everything between, have a lot of temporal activity or less, spatial activity or not, as we look at these plots of SI versus colorfulness and SI versus TI. Okay? Now we don't use these going forward, it's just a demonstration that our videos nicely span the spaces of content. Then we took these, as I said, and we downsampled them to 24, 30, 60, 82, 98, and of course 120 frames per second, which matches our display's refresh rates. We compress these using the VP9 codec. This is one of the big three, the other being H.264 and HEVC. VP9 is used to stream billions and billions of bits of YouTube every year. That's what YouTube uses to compress videos. Netflix also streams VP9, and VP9 is also very closely related to AV1, which is a next generation standard. The three standards, they're VP9, H.264, and HEVC. These are all hybrid codecs. They're actually very similar. So the results of our study apply, in our view, generally to all of these types of compression. And we're primarily, studying temporal frame rate effects. We compressed at 5 levels of compression, or 5, CRFs. You might think of acute quantization parameters. These are broadly spread. It includes 2 extremes. One is very little compression, that's the highest CRF value, and one is extreme compression, a very low CRF value. And we did that because, well, first of all, that gives a broader spread of compression levels. Having a broad spread, we have found over the years, helps us build better models. Also, if we consider compression that's very negligible, that enables us to focus on the effects of frame rate in those instances. And when compression is very large, we can explore, well, if we have high compression, does frame rate really matter? There are instances, for example, in wireless streaming where sometimes the compression is very high. And furthermore, this widespread again helps us build better models um, rather than just using a narrow range of parameters. So overall, we have 6 different frame rates, 5 different compression levels, 16 contents, a total of 496 test videos, including the originals, which were viewed by the human subjects. That's a fairly large number. Most studies done in the laboratory, like this one, are about half of this size. So this is a very extensive study. The nature of the study was what we call a single stimulus, meaning we show just one video at a time to the subjects. I believe this is always the best way to do it, except for some very particular circumstances, because it better reflects real viewing by human subjects of what they are going to see out there when they're watching television. Also, it's very hard to compare 2 videos that are side by side playing in time. So we always do video studies as single stimulus. We had 85 subjects who participated. Each one of them would watch each video and then assign a single score using, you can see this sliding interface here on the lower right. We'd watch a video and then rate it as anywhere along the scale that they like. Each video received about 40 human scores. 40 instead of 85 because we used a round robin where we shifted through the video set as we moved from subject to subject. That way we get a greater diversity of opinions per video, and we don't have to show the humans 85 videos and all their, all the videos in that way, because that would take a much longer period of time. We limited it to 2 40-minute sessions because after that, the subjects start to get fatigued. And we didn't want to go to 3 sessions unless we had to, which we didn't. This shows our monitor parameters. It's a 4K. It's a pretty good size. All the numbers are there. We collected mean opinion scores. MOS. You'll also see the term difference mean opinion scores, but I'll talk about just MOS first. What is a mean opinion score? It's very simple. It's the average of the scores assigned to each video, by all of the subjects who viewed that video. Okay, so in our scale of things, 0 would be the lowest, and 50 would be the highest. We used a scale of 0 to 50. So 50 is a very high quality video. 0 would be a very low quality video on this scale. I'm sorry, this is, confused myself, 0 to 100. And this is the scale of MOS. This is the histogram of MOS values. So most of the MOS values, most of the quality scores are in the range from 50 to 60. There weren't as many poor quality videos and not as many very high quality videos, which is great. We like this kind of distribution of MOS scores. The second plot here is very interesting and it's very important because what we did was we took the group of 85 humans and divided it in half. And then we took we computed the correlations between the MOS of one group versus the other group. And the reason we do that is we want to see how much humans agree with each other about the qualities that they gave, the labels that they applied to the videos that were shown to them. And we plotted it here as a scatter plot. You can see it's almost a straight line. It's really a great result. Naturally you don't expect a perfect straight line because humans don't agree with each other exactly, but there's not a very high variance around the scatter plot, which is wonderful. And we found that the humans had a correlation between the two halves of about 0.96. We did this many times using different divisions of the human subjects, and every time we got a correlation of around that value. Okay, some other interesting observations. First of all, we found that the quality scores that were given by the human subjects, meaning the MOS, and this is actually the average MOS over all videos at a given frame rate. So that's why it's, MOS is already a mean, but this is the average of those mean values over all the videos for each frame rate in the study. So what we found was that videos that had no camera motion in them had higher quality than videos that did have camera motion. And in both cases, as the frame rate increased, the average reported quality also increased monotonically in the case of no camera motion, almost monotonically in the case of camera motion. Okay? So we divided the videos into two sets, one where the camera wasn't moving, one where the camera was. That separation is very interesting because it tells us that when we have a lot of motion in videos, then you tend to see many more temporal distortions like stutter and judder. A big separation there. The curve for camera motion wasn't quite perfectly monotonic. That's just probably a little bit of a statistical aberration. It's almost monotonic. It's just a little blip downwards. And there's no other explanation for it than that. This is a pretty high frame rate. Now, it's very important to understand that even though the videos have a almost monotonic or monotonic increase in quality with frame rate, that doesn't mean that you can just take frame rate and predict quality from it. Not at all. It depends so much on what the content of the video is, and that's what this plot shows. The horizontal axis here is the indices of the 16 original videos. For all different videos that were derived from those original 16. This shows the average MOS scores for each of those videos, with the vertical axis being MOS and the horizontal being the video index, and the colors indexing the different frame rates. Now, as we expect, on average, the highest frame rates had a higher quality, as you can see by the uppermost blue curve. The lowest frame rate had the lowest quality because you start getting stutter and judder and that kind of thing that is very undesirable. But it's all mixed up otherwise. You cannot say that, okay, because one video has a higher frame rate, that it has also a higher quality. So for example, these very high frame rate videos here in blue have lower quality than these lower frame rate videos, red, purple, and yellow over on the left. So it's actually a very complex and complicated thing to decipher, which is why we need to do all this work. Otherwise, it'd be trivial. Instead, it's very hard. Why is it so important? Well, because, as I said, streaming companies compress videos. They have to save bandwidth, to save cost, to be able to fit the videos down the network pipes in real time so that you can view them at home. Now, the way that they do that these days is they compress videos on a per scene basis, from scene to scene to scene, in an adaptive way. So on each scene, they try to optimize the trade-off between the number of bits for that scene versus the measured perceptual quality or the predicted perceptual quality, using an algorithm like SIM or VIF or VMAF or some other perceptual algorithm. This is what's done today. Now, with the advent of very high definition videos, they now use downsampling as part of compression. So not just H.264, HEVC, or VP9, also downsample. Hey, if you take a video that's HD and downsample it to, if it's UHD, you downsample it to HD, or same thing as 1080p, you have multiplied your compression by about a factor of 4. So if you can get away with that without affecting perceptual quality, is very desirable. And it works, and that's the way it's done right now. Now, why can you do that? Well, sometimes a video, when you downsample it, looks the same, just as high quality. What really happens, by the way, is that it's downsampled and then compressed, transmitted to your home, decompressed, and then upsampled back to UHD for your UHD television. So it started out at UHD, but was downsampled along the way. But if they make measurements on it that say it'll look the same, then they will feel free to actually downsample it before upsampling it again, which is okay because sometimes videos are smooth and don't need UHD, at least on parts of them, maybe on a per scene basis. Likewise, some videos need HFR to avoid things like stutter, things like live action, live sports, things like that. Whereas other ones don't need HFR. They can be streamed at standard frame rate, even if the original is HFR, and then upsampled again at the other end, if so desired, to a higher frame rate. In the movies, you don't see much stutter in the movies in cinema, and that's because cinematographers, colorists, and editors would take precautions to avoid that, to avoid, rapid camera movements and that sort of thing. Because in the movies, it's only shown at 24 frames per second, although it's each frame is shown twice in a row. So in other words, temporal downsampling can be part of compression, and people are looking at that, and this database that we've created is the tool to be able to create algorithms that can determine how much you can compress videos while also downsampling them in time. Okay, second part of this talk is we created an algorithm called the greed algorithm. It's greedy for bits, greedy to save bits by measuring video quality as a function of frame rate, while also as a function of compression. Again, this is work that was led by Pavan, a graduate student in Live, and our collaborators at YouTube also participated. So before I describe greed, I'm going to talk about an older model briefly called VIF, or Visual Information Fidelity. This algorithm supplies most of the features used in the Netflix VMAF algorithm, which is used to control the quality and compression of every single video that is streamed by Netflix all over the world. It works in the following way. If you have a reference video and a test video, a wavelet transform is conducted on these. This is very much like the way video data is processed in your visual cortex, in your brain. Then, based on what's called a natural scene statistic model, local statistics are computed, local entropies on each of the videos on a patch basis. And then these local entropies are first scaled and pooled in certain ways that I'll talk about in the context of our model, and then they're compared between the reference and the test video. So everything is based on entropies under a natural scene statistic model. The method of comparison in VIF is just to take a difference, absolute value, and then to do some more pooling. By pooling, I mean, combining over space and time into just a single number. And I'll talk about some pooling methods in a minute as well. So I won't go any further into VIF, but I will, talk about natural scene statistics. If you want to read more about VIF, here's a citation for you. It's an information theoretic approach to video quality measurement using perceptual principles. Underlying VIF and VMAF and greed is a very famous natural scene statistic model. As I said, we conduct a wavelet transform of the videos, which is a form of bandpass operation. Bandpass processing of pictures and videos gives results which invariably obey certain statistical laws with high regularity. It's an amazing property of visual signals of the natural world, that if you bandpass filter them with a well-behaved bandpass filter, they will obey certain statistical laws, unless they've been distorted in some way, which is great for the field of video or picture quality prediction. It turns out that these statistical models are altered when distortion, such as compression, or maybe even frame rate changes are present. I'll also mention that not only do these statistical models apply to pictures and videos, I haven't described the model yet, they also apply to frame difference signals. And that's used in another algorithm called the ST-RED, or space-time red video quality index. The model is very simple. If we take a video or picture, and we bandpass filter it in space and or time, or maybe with frame differences. Then if we compute the histogram of the results of that on a frame basis or a temporal basis or both, space-time basis, those coefficients will obey a generalized Gaussian model with great regularity. A generalized Gaussian is something very much like a Gaussian, except it has a different exponent in it. So you can apply a bandpass operation to your visual signal, then try to find the best fitting generalized Gaussian model to that resulting bandpass video. And the results can be very useful. When you find that best fit, you find these parameters alpha and beta. And there's various methods such as maximum likelihood for computing the best fitting generalized Gaussian fit to the histogram of the bandpass signal. So now I'll get into greed a little bit. So greed has two parts. One is called temporal greed, that's measurement of temporal quality, and the other is called spatial greed. Temporal greed is a little more interesting to us now because it's kind of the new topic where we deal with frame rates, and it's a little bit more complicated and sophisticated too, as you might expect with the higher dimension. We compute the two indices and then we use both of them in a learning framework, as you will see. So first, temporal greed. Temporal greed. Okay, so how does temporal or T greed operate? Well, here's an overall diagram, but I'll just go into the details. We start in a very simple way. We take our video, which is a function of space, which is boldface X, and time, which is T, and we apply to it temporal bandpass filters, meaning filters that are a function of time only, specifically capital K of these filters, indexed from 1 to capital K. Okay, actually this should be little k here and big K here. So capital K of these filters we apply to the signal. Now, this approach works pretty well with a lot of different bandpass temporal filters. We tried 3 that we talk about in this. First of all, Haar filters, second of all, Dobeshay filters, and thirdly, biorthogonal bandpass filters. Each of these has some nice properties. Haar filters are very simple. They're basically just, like step functions and things like that. They're super fast to implement. The Dobeshay filters are basic wavelet functions that have very nice interpolation and approximation properties. The biorthogonal filters are likewise wavelet filters that can be designed to be symmetric and also have very nice approximation properties. We'll try all of these as we go later on in the experiments. So as I said, when we bandpass filter a video, it's going to obey a Gaussian or a generalized Gaussian model unless it's distorted. You can pretty much rely upon that as long as it's not been distorted by some sort of process. The algorithm works as follows. Each frame we break into patches, typically squares, that are radical m by radical m. We're using radicals here, so we can just say, well, there's m pixels within each patch. Okay, so break it into patches containing m pixels. This is after bandpass processing, mind you. Okay. So then we define, once we've done that, we can index these patches over space and time and by patch, okay? To form coefficient vectors from each patch. So each patch has a vector of coefficients, B, indexed by K, where K is which bandpass filter, by P, which is which patch in the frame, and T, which is which frame, okay? Each one of these vectors, which is multidimensional, of course, contains m values we model as obeying a generalized Gaussian distribution. But we go further and we assume that that observed coefficient vector B is one that has been distorted by noise, a neural noise. Why do we do this? Well, this is intended to model the imperfections of our vision system. Our vision system is definitely not perfect. The lenses are imperfect, the neurons are imperfect, the whole process is imperfect, and the brain somehow deals with that imperfections and the actual neural noise that occurs, but it does affect our perception, including our perception of quality. Our model is super simple. We just call it Gaussian white noise, but including that model significantly elevates the performance of the method. It's just a way of incorporating uncertainty in the model. Well, under the generalized Gaussian distribution, the entropy has a closed form. Once we've found that best fitting GGD using some method of curve fitting the generalized Gaussian to the histograms of the patch coefficient vectors, histograms, this is the closed form expression in terms of the two parameters, alpha and beta. I'll go back and show it in the generalized Gaussian model, this parametric model. We make the measurement of the histogram, but then we scale it. You can see the same entropy H here for this given patch in the lower right, but then we multiply it by a scaling factor. It's basically multiplied by the log energy of the patch. So sigma squared is the sample variance of the patch we can think of as energy, and it's a way of improving locality by giving a higher weight to regions of the image which have higher energy, more motion or more activity. And it works. It also elevates the performance of the algorithm. So what I'm going to show you now is bandpass versions, temporally bandpass versions of the same videos I showed you earlier. So on the bottom, 60 frames per second. If I apply a simple bandpass filter, I used a Haar wavelet filter. To this, you get something that looks like this. It's, it looks bandpass because it is, grayed out and that sort of thing. As the camera moves around, you can see that the nature of the video is pretty smooth. Not perfectly smooth, there's some shadowing effects and so on, but things change pretty smoothly in the 60 frame per second video. In the lower frame rate video, and hopefully you can see the differences between these from a distance in space and time. In the lower frame rate video, you can see, well, things are much more jumpy and chaotic. You can see intense shadowing and it's very discontinuous over time. And that is reflected in the statistics of the bandpass signal. It is reflected in the entropy, which becomes measurements of a much more chaotic type of process. We can use this as we go. Here I'm showing histograms of the bandpass coefficients of the videos. In fact, the colors here again code frame rate. So the red curve here, for example, shows the histogram of all the 60 frame FPS videos. And you can see that, and these are just the original videos, not even compressed. You can see that frame rate changes the entropy, even aside from anything we know about distortion or maybe temporal distortion or something. Consistently changes the entropy. It's just a statistical effect impacting the entropy when we modify the frame rate, which may not reflect the distortion information that we're looking for. In other words, changing the frame rate introduces a bias into the bandpass histograms and therefore into the entropies. However, recognizing this bias, we apply a way to compensate for the bias. Here's another way of seeing the bias. So as we change frame rates, the scaled entropies that I talked about, remember these guys here, down here, scaled entropies at the bottom of the page. These are very different at different frame rates, but this is not just because of distortion. Okay? So what we do is in the greed index I'm about to describe, the temporal greed, we have a bias factor that accounts for this bias. So the algorithm can focus on the perceptual aspect of changing frame rates. So in this process, in temporal greed, which I'll give you the algorithm in just a moment, I just want you to know that there are 3 videos that are used in the algorithm. One is the reference video, of course. That's the high quality video that we're comparing against. Another is, of course, the distorted video. This is the video we're trying to predict the quality of, where we've applied, compression and temporal downsampling. It might be used in a compression setting to decide, well, should we send that video with that level of compression and downsampling? The third is what I call a pseudo-reference video. Okay, and what the pseudo-reference or PR video is, it's just the original high-quality video that has been downsampled to the same frame rate as the distorted video. So no compression. It's been downsampled in time dimension, to the same frame rate as the distorted video, but it has not had the compression applied. The distorted video has compression and downsampling. The pseudo reference has only the downsampling. So it is distorted, but only by temporal downsampling. Okay, why do we use this? Well, it allows us to cancel the bias. So again, this is the entropy term, which I described before. Entropy over patches, P, for each bandpass filter and each frame T, scaled by the energy of the patch, log energy of the patch. We compute these quantities, this epsilon, for all 3 types of videos, the reference and the distorted and the pseudo-reference videos. And then the algorithm is the next equation. So for one bandpass filter, we'll go ahead, later we'll combine these terms, but for one bandpass filter, at one frame instant T, the T-greed index for filter K and time T is this expression, which is a sum over all patches in that frame. In that expression, there are 2 terms of interest. One is the one in absolute quantities. That's the epsilon super D minus epsilon super PR. And the other is the ratio. The first one is the bias removal term. And I'll explain that in a second. But basically, if there is a difference in frame rates, it's accounted for by this term. The ratio term accounts for the perceptual loss at different frame rates, and of course, from compression. So here's a little explanation for what happens by the extreme cases. So this is the full term at the top. This is the T-greed for filter K and at time or frame T. If it turns out that the reference and distorted videos have the same frame rate, okay? Well, then the temporal greed index loses the ratio term, and we only have the difference between the 2 values, okay? If there is no compression, then because the distorted and the pseudo-reference are now identical, the ratio term disappears. And we only have, I'm sorry, the difference term disappears. And we only have the ratio remaining. Okay? Of course, if all 3 videos are identical, then the T-greed index is 0. Okay? So if there's no compression, T-greed accounts only for distortion from frame rate changes. Otherwise, it accounts for both. Okay. Spatial greed. Remember, there's 2 parts, and we combine them. Spatial greed also involves bandpass filtering, but it's much simpler. It's very simple, in fact. At each frame, at every pixel, we subtract the local mean value. Okay? So within a neighborhood of that pixel, we form a weighted mean of the pixel values and subtract it from the video. That's a very simple bandpass filter. The window we use is a Gaussian kind of shape, very Gaussian-like, which is very common. And this bandpass process is the basis for many popular image quality models, meaning still pictures, such as the Brisk Index, the Nike Index that are used all over the world for no reference picture quality prediction. These bandpass signals, these are spatial bandpass signals, also obey the GGD natural scene statistic model. So we can do similar processing from there. Even though these are not directional, these are, it's not a pyramid of any kind in spatial frequencies. It's just simple, removal of local mean values. So we can again compute entropies based on the GGD model, multiply it by the local log energies, this time in space of the signal. Let's call that theta. There is no K because there's only one bandpass filter. It's center surround filter. Since the Gaussian is isotropic, then the process of subtracting the local mean is also isotropic. But we do compute it on a patch and on a per frame basis. The S-Greed value for each frame is very simple. Just take the differences, the absolute differences across patches between the reference and distorted videos of this value. There's no need for a pseudo-reference, no need for debiasing. Okay, so now we'll take these outputs, very simple processes, very fast computations actually, and we will pool them and then feed that to a learning engine. The S-Greed values we sum over all frames. The T-Greed values we sum over all frames, leaving us still multiple versions indexed by K, which is the different bandpass filters. We won't sum over the bandpass filters. We'll keep all of these at different, say, different spatial orientations. Okay? So the spatial index only captures really spatial distortions, from compression and blur. The T-Greed index, and by the way, this should be a T here, I just noticed that little error. It captures both spatial and temporal distortions, such as judder and stutter and that sort of stuff. Strobing effects, motion blur. So we get both spatial distortion information and temporal distortion information. Then we train an SVR with these features. So the features are S-Greed, and then the K values of T-Greed, and the human labels applied to each video. The human labels applied to each video. Okay. So the features, by the way, we tried, as I said, Haar, Daubechies, and bi-orthogonal bandpass filters for the time for T-Greed. We computed a 3-level wavelet packet transform. That's 7 subbands, so big K is 7. So there's 7 of these T-Greed values. Entropies are computed over 5x5 patches. We just use those. It could be that other patch sizes might be advantageous. And we conducted this over 2 scales. In other words, we took the videos, we downsampled them by a factor of 2 in each direction. This is a simple way of getting more multi-scale processing in there. So in other words, we just doubled the number of features. For spatial greed, similar. We computed those entropies over same size patches. We did everything at 2 scales by downsampling every video by a factor of 2 along both dimensions. Gives us more features. Summarizing, there's a total of 16 features, not terribly many. All of these features are pretty fast. Removing the local mean is fast. The steerable pyramid is very fast. So this is a fast algorithm. There's 2 spatial features because we have 2 scales. There's 7 subband features because we have 7 subbands that are in the temporal dimension times 2 scales. So that's 14. And then, of course, we have the human labels, 1 for each video. These are all fed to train a support vector regressor using an RBF kernel, trained and tested on the live database, which has those human labels. A little bit of perception, just to reinforce that this is truly a perceptual algorithm. We use a center surround retinal model. In fact, that subtraction of local mean is very much like a difference of Gaussians. We use spatially relevant natural scene statistic models. Temporal model uses a cortical model, a lateral geniculate nucleus model combined together, temporal filtering, space-time filtering, which nicely model what happens in our visual brain, along with a space-time natural scene statistic model. You might be wondering, what about the temporal contrast sensitivity function? You may have heard of the CSF, and you're probably familiar with the spatial contrast sensitivity function, which describes the overall bandpass nature of the human visual system. Well, this shows under different lighting conditions what the temporal contrast sensitivity function of the human brain is. And we didn't incorporate this directly, but by feeding different bands, different values k of T greed into the algorithm, multiple frequency bands, the support vector machine, we left to figure that out. Okay, our experiments. In the database, we divided it into 70% training, 15% validation, and 15% for testing. We did it 200 times with random splits, always keeping separation between content. So the same video content would never share in any two of these subsets. We computed performance against human opinions using two different correlation measures, the Spearman and the Pearson's. These are standard methods for performance of quality algorithms. And we did this 200 times over 200 random splits, report the median performance. What we found was that the new algorithm greatly outperformed the older algorithms like VMAF, which is so widely used, and SIM, which is very widely used. A correlation of 0.88 compared to 0.77, which was achieved using the bioorthogonal ones, that's the ones that we recommend, is very significant. It seems like only beating by 0.1, but that is a huge boost and will account for saving many billions of bits of internet traffic, because it's in the middle range of qualities where the algorithms are very different. At the boundaries where you have a very low quality, very high quality, any algorithm can do a fair job in those instances. So a big boost in performance. Somewhat surprising was that the old PSNR did pretty well compared to VMAF on this database. It never does on any other database. Why did it do okay here? Well, I'll talk more about that in a minute. You notice that the greed algorithms, these are the three greed algorithms, higher performance, and the bioorthogonal greed had a very narrow range of outcomes. So very reliable, very stable, as well as very high performance. So we recommend that bioorthogonal wavelet, just like is used in video compression. We also studied it by bit rate, and at every bit rate level, the new algorithm significantly outperformed the other algorithms, especially at lower bit rates, where we start seeing those temporal distortions, where the huge outperformance of about 0.82 or 0.84 compared to things down to the 0.2 area, because these algorithms just can't assess quality from temporal distortion. In fact, that's why these famous algorithms like VMAF underperform PSNR, is because they incorrectly report performance. Because you may have a video that has a very high quality frames, so these algorithms report a very high quality very accurately, except the overall video is very distorted by temporal distortion such as judder. Ironically, because PSNR doesn't report the spatial quality as accurately and tends to be more off or misreport, it actually gets higher correlation, although still terrible. 0.48 is terrible compared to 0.82. So last remarks, frame rate is important. It's going to be very important in compression going forward because the content is going towards high frame rate in various areas such as sports. Cameras and displays are already there. We just need compression algorithms and quality measurement tools to be able to account for higher frame rates and different frame rates. We foresee these kind of methods, like I've just described, being incorporated in workflows of companies like Netflix, Amazon, YouTube, and so on, to control temporal subsampling as part of the compression workflow. We've shown you can accomplish this using perceptual principles and statistical principles maintaining a fundamental approach throughout. These are our sponsors. We're lucky to work with most of Silicon Valley that's involved in video streaming and video social sharing. YouTube, Oculus, Amazon, Facebook AI, Netflix, and Video Clarity, and also ETRI in Korea. We worked with for the last several years on similar problem as this, but also involving spatial subsampling, a topic of a later talk sometime. Just to finish, I'll show a visual illusion. Here's my giant car because I'm a big guy. My wife's car, she's not as big, and my daughter's car is much smaller. But I want to show you something because when I move the car, by the way, why am I showing you this? Because I'm a big fan of visual illusions, and I always show a visual illusion at the end of my talk just to reinforce how important and mysterious perception is. Because look, as the car moves, it's just as big as my car. And I didn't play with it. I just shifted it over. Amazing, huh? Anyway, everything about visual perception is amazing and fascinating, and it's great to have engineering applications to that. I hope you enjoyed the talk. I'm available for any questions. I guess they're going to set up some kind of chat session. Anyway, I'm done. I know I went a little over, but it's a big topic. Thank you so much for having me. And I will stop recording.